Chebale, Jambo, habari gani? Mzuri sana. I am Dr. Marcelin Dabo, an African from Senegal, West Africa, a PhD on control systems, and a consultant engineer in industry and an independent researcher. So today I will be going to talk to you about an interesting concept that I have introduced for second order dynamical systems in the sense of ordinary differential equations. And then also you will be able in my YouTube channel to see some previous videos that I have presented about first order systems and also second order systems. So based on some specific concepts that I have introduced, I will be today talking to you about how you can do just identification of a second order system. So now let's go. So for dynamical systems that I will be studying, I will just make use temporal approach by time. I will not be talking about transfer functions. It is a choice. And then I find that with the temporal approach, I have been able to derive or to calculate and to compute so different results and interesting results that are very useful, okay, for an engineer, for a researcher, in terms of computation, for example, of temporal performances or performances regards to time. Okay, this is what I will be talking about. So now let's go. If you consider second order dynamical system written like this, where you have here at the right part of this equation, B over A0, that is equal to the static gain. The E of t, E is the entrance, t is an implicit variable of time, sorry. And then the output that we have here is S of t, you have S dot and S double dot, and these coefficients are what I have defined as A1 over A0, like the natural time constant. I invite you to go and check the previous video before this one. You will be able to see all the different definitions that I have given in detail. And then in details, and then here, the time constant, surface, time constant of the surface of time. This is what I have defined also as A2 over A0. And then by proceeding by identification from this expression to this one, or this expression in regard of this one, we have that the tau tau is equal to 1 over omega n squared. The tau n is equal to 2xi over omega n. And then the relative time constant that I have defined here is equal to 1 over the double of the products of xi damping ratio times the natural pulsation. This is exactly what I have defined as being as the half of the time constant of my own dynamical system. Okay? So again, if you go to the previous videos, you will be able to see what it is about in details. So now you recall that when you have a dynamical second order system, it depends how you write the solutions, and then the solutions depends also on the values of the damping ratios that you have here. And then for this study, we will consider just the three cases that you have here. We will not consider the xi equals 0, okay? So for a non-damped system, the expression for an autonomous system means that the entrance is equal to 0, and then you take the initial condition from its equilibrium position, and then when you release, the system go to its equilibrium. So just a comment, I will be talking about dynamical systems that are only stable, meaning that the time constant is strictly positive, okay? And then as said, it's only the temporal approach, so no transfer function. So all these expressions are common in a certain sense. For example, you have an exponential that is always the same here. You have the initial condition that is present also here, and then you have a given function of time. Okay, so this function of time and also the damping ratio is, for the case of an underdamped system, is given in a trigonometric world, meaning that we are using the sinus here. Okay, just a reminder, I want to give a big honor and a big clap to priests of pharaonic Africa that we call Kemet, the black priests, who had received, they received Pythagoras. And then the so-called theorem of Pythagoras is not its theorem, it is a theorem of the African priest, because they knew it at least 1,000 years before Pythagoras' birthday. Okay, 1,000 years before Pythagoras' birthday. And then when Pythagoras came to Africa to study, he spent there 22 years. Okay, and the priest taught him so many details and so many things. That was a comment. So here, when you consider a system that is critically damped, you have the same structure with this function. Okay, 1 plus xc omega n, it is a function, a affine function of time. When you consider this last one, you will see that the system is living in a hyperbolic domain. Going from an underdamped to an overdamped system through a critically damped, you can see that the functions are varying, or the worlds of application are moving from a circular world, going through an affine world, and then finally to a hyperbolic world. As I said in a previous video, if some mathematicians are listening to me now, you can see that it can be very interesting to consider that. What is a transfer function, or what is a transformation function of transformation, not a transfer function? What is a function of transformation is that will allow us to go from a circular to an affine function. After the affine function, we go to a hyperbolic function. So this reminds me so much the conics that I have studied some more than 20 years ago. And then in Senegal, West Africa. And then here, so for for what we have here, so we have here the exponential of xc omega n, but you can see that if you take t minus td, you divide it by 1 over xc omega n, you have the same result, and it is the same thing as this one for a first order system. This is why I emphasize again that the time constant in the sense of Dabo, me, for a second order dynamical system is defined as 1 over xc omega n. Okay, so let's go. I think that these things are clear. If you want more details, you refer to a previous, as I was saying. So if you consider these previous expressions that you have seen, we consider that for any dynamical system that is moving, it reaches a certain percentage of the equilibrium of its given equilibrium at a certain multiple of its own time constant. The philosophy or the paradigm is exactly the same for a first order system. Okay, so going from this expression, what I have done is I have introduced and calculate everything like this. Okay, and then from there, what I have done, I have a gamma function, and this for any other given, for the overdamped here, critically damped and underdamped systems. And then what you do with this, you have a function that I have defined as a gamma, that is a percentage of the output of my autonomous system divided by the initial condition, exactly as for the first order system. And then from here, you make the alpha r, that is a coefficient, that is a coefficient of the time constant. You make it move, okay? You give him different values, and then you will have different values of the percentages of the signal according to its initial condition, in the case of an autonomous system. And then with that, you will be able to define your alpha r, and from that alpha r, it is possible to define an identification criteria. So I have presented an identification criteria in my YouTube channel for first order dynamical systems. And then from there, so I took the same vision and the same philosophy. Just to show you, this is a criteria for dynamical systems of first order, okay? Because if you consider a given t response time here related to the departure time here, all time that you can have, all time responses that you can have for a given first order system are a multiple of the time constant defined for a first order system. And then if you consider the ratio like this is a criteria that I have introduced for first order systems to make identification. And then you just consider two different times and then you compute their ratios and you will end with a constant. And then if you consider specific percentages of the initial condition, you will be having some constant value, and that constant value will not change. For example, if you fix the ratio, so here it is for second orders, but the ratio for first orders at the same percentages of the initial condition, okay, are given here, right? So if we come back to this expression, for a second order system, it's the same paradigm. And then going from there, we end for a critically damped system with this ratio that is equal to these values, as you can see. For example, ratio for a second order system for which the damping ratio is 1, between percentage 90% of the initial condition and 10% of the initial condition is equal to 0.136. Okay. And then you have these values for the others. Okay. So this is just a reminder that I have put here. It is the same paradigm as I was saying for a first order system. We have here the difference, the time response relatively to its departure instant, to the departure instant of our system. It is a multiple of a time constant of a first order system. And same thing for a second order system with a time constant defined in the sense of me, of Dabo. And then for the different damping ratios, like for example here, for Xi equals 1, this is what you have like a constants. And then I have resumed everything here from 0.1 as the damping ratio to the value of 1.95 that you have here. So the damping ratios should be read by column. Okay, for example, if you have here Xi equals 0.1, you have the ratio here that is corresponding to Xi in the same column. That will be the same here under, because we don't have place to just make one board in our book. So this is an extract of my book that I will be talking to you later in this presentation. So if you consider the Xi, the damping ratio here, you have here Xi of 0.55. And then with this value, you have the different damping ratios, the different coefficients, okay, for the identifications that you have here. Okay, so this is my book that will be appearing very soon. And then this is, of course, the French version, but the English version is coming also very soon. Okay, so thank you very much. So don't leave, because I am going to present you some simulations, as I do always. And then for these simulations, we're going to check them very quickly. So we consider here our second order system, okay, in Simulink. And then here what we consider, we will drive this second order system from here, okay, the MATLAB. What I do is I consider the same range. If you look at this presentation again, what we have in these tables is that I just take different values of the damping ratio by step of 0.05, going from 0.1 to the value 1.95. And then for each given value, I have computed the corresponding ratios as constants. So if you have a given problem that you face too, and then they give you the damping ratio, and then you want to compute the corresponding alpha to have, meaning the corresponding coefficient or ratio for your dynamical system, for the identification of your dynamical system. What you do, just go back here and then see that to compute here the corresponding alpha coefficient to a given gamma, that is a percentage of the output related to the SDP, you will have here, you will fix the damping ratio, and then you take alpha as a variable that is varying. Okay, you can make it vary from, let's say 0.01 up to, you can go from 0 and you do steps of 0.01 and you move up to 12, up to 20, and then you see what will be the correct values for you. This is how you do it. And then if you have the graph, you take, for example, a position on the graph, and then you move it and check for the corresponding gamma for any given alpha that you have. Okay, this is how it works. So going back to MATLAB. So now here I was saying I give you a range of damping ratio, and then from this range I just take one of them, okay? And I will not be knowing them by myself because I will not be displaying them in this program. I do the same for the natural pulsation, and then I will do the simulation going from this place, okay, to simulate this program. And then by simulating this program, I will just take an initial response. And then from that, I will plot the graph. And from the graph, I will try to define the static gain. I will try to define also the damping ratio and the natural pulsation. So to identify completely my dynamical system. Okay. So now these are, I did it with my own method. Huh? So you see that it's relatively simple. So now let's go for the app. I evaluate the function. It will be going, it will be plotting, it will, okay, so now the plot is done. And then here, what you have is a given system. So the static gain that I can see here, I just take the output here. Okay, it is equal to 1.5. The input is 1, so I can say that the static gain is equal to 1.5. Okay, that is the value of the static gain, 1.5. So now let's check what we have here. It is exactly 1.5. This is what we have here. Okay, because I take a random here, and then finally I take the value. Okay. So now let's go for the computation now. So we are going to check for the damping ratio. So as I told you, we can position ourselves on the transient only. And then let's go for 5% of 1.5. This is 0.075. 0.075. No. Okay, let's consider it is it. So the corresponding time at 5% is equal to 0.0375453. Okay, this is what we have. And then if you go for 95%, we will be having here 1.425. Let's go for 1.425. So here we have 1.25, and then the time response at 95% of the equilibrium is equal to 0.573545. Okay, this is what we have. So if you compute the ratio, we will be having this value 0.0655. 0.0655. So this is the ratio between 5 and 95%. Let's go to check the table. We say 0.065. Where is it? It is here. So I can, with only this one ratio, say that my damping ratio is equal to 1.1. Okay? As you can see here. If I want to confirm, or if I am wrong, I can also calculate this value of damping ratio, this value of the discriminant, okay, the criteria, okay, this ratio, I can compute it also and check if I will get this value and this one, of course, I think I will be getting them. I will be getting them. So if I go back to my computation here, I can say that my Xi is 1.1. So if I check it, because it has been computed here, if I check the Xi, I will have the value that I was waiting for, that is 1.1. From this value 1.1, I just can check how I can derive now the time constant, the corresponding natural pulsation. If I check that in my notes, I just have to do something to go and take the value, because the time constant will be positioned somewhere on the graph. Okay, somewhere on the graph. And then it is positioned according to my notes at 1 minus 0.78, that is a percentage in the complement at 100%, of 1.5. So the time constant, it is at 0.33. So let's go for 0.33. Okay, let's go for 0.33. And then for this value, we have, at this value, we have the tau that is equal, we can read it, equal to 0.094, 64, 53. This is the time constant, the tau in sense of Dabo myself. And then now when you have this, the omega corresponding that we can derive is equal to 1 over, okay, we put here tau times C, and then the omega that we have derived is equal to this value. Let's now check what is the value that have been computed here, for example, okay? Because we have randomized the values that have been computed here. Let's check, it will be the same. So you can see that it is quite the same. It is 9.6 here. You can say that it is also 9.6 here, okay? This is how you can derive all the parameters of your system, okay? And then from this, what we have seen is here we have an initial condition. There is something that I want to check. Yeah. Okay. We had the initial condition that is equal to 0. Okay. Both of them are equal to 0. As you can see it here. The initial conditions are here, so you have them. And then from what I have done, we can see that we can derive very easily. We can also position ourselves in another place. Okay. And then from here, what you have, for example, this percentage, let me just recall that which value, yes, for example, at 95%, 1.425, let's go for 1.425, what we will be seeing there, okay, is this value that we had. So from this value, for example, that corresponds to 95%. Let me check again in my notes how to compute the omega n from this value. And from my notes, if you have a damping ratio that is equal to 1.1, what you will be having at 95%, I will take, to have the omega n, the following constant that is equal to 5.491 divided by the corresponding time that I have there, that is 0.573545. You can see that your omega n is quite the same with what we have computed here. Okay, so you can see that it is possible to have to use this method that I have introduced in order to do identification of second order systems. Okay, so now let's go again. So before we go, you see that you can have a second order dynamical system, or you can have any dynamical system with the initial conditions that are equal to 0, and then you don't know, or you can just have a result. Okay, you don't know that this result is a second order or a first order dynamical system. So if you wanted to derive this, and if the damping ratio is equal, is between 0.1 and 1.95, of course I will be able to give you the different ratios that you should have, or also, as I shown you, you will be able to compute them, okay, in an easy way normally. But please understand that if you have another damping ratio, it can be also possible to go, and that is different. You can check, you can make the different operations, okay, to find again your different alphas multiple of your time constant, for example. But you can have a number of data like this registered, for example, somewhere, and you come to see your number of data. You don't know what is the first order, if it is a first order, if it is a second order, but it can look like, for example, a second order. And then you can use the methods that I am presenting to you. You refer after to the tables that I am resuming in my book to appear. And then from the tables that are inside, you will be able to find your own damping ratio, as I said. So now let's go again and do a second example to show you uh, how efficient this method is. Okay. So I clean everything. And then from here, thank you. Thank God for this, how you say it, this result, because I wanted to have something like this, okay, with an overshoot. And then here you have also the static gain that is equal to 1.5 divided by the step, that is 1 here. If the step could be 1.2, of course you should divide 1.5 divided by 1.2. But here the static gain is this, and then if you take just B2 as I shown before, you can have this. So now from here we check the transient response. Here what is interesting, somebody can just jump here, okay, compute the percentage of overshoot, according to the equilibrium, and then from there decide that this is the given, this is the corresponding damping ratio. But what we are going to do here, we are going to do it like we do previously. We go to consider the 5%. So 5% of 1.5 is equal to 0.075. Let's go for 0.075. Let's consider this is good, and then the time that is given at this moment is equal to 0.034, okay, 0441. I just want all these values because I just want to have more precision. And then if you go for 0.95, we have 0.425. Let's go for no, 1.425. 1.4 1.425, and the corresponding time at 95% is 0.201944. So if I go for this ratio, I will be having 0.1686. Let's go to check here in the table what we have. 0.160, somewhere here. We said 68. So the damping ratio, I think that it is equal to 0.35. Okay, let's come back to our system. Let's come back to our system. And then we check here. We see that we have 0. This one. So I say that it is 0.35 according to my table. 0.35 here. Okay. And then if you come back to MATLAB, just hit here C. You have it here, right? And then from here, from this 0.35, I am going to derive also according to my notes, 0.35. Okay, it should be, the time response should be localized at a percentage of, let's say, 1 plus 0.2671. Okay, and this is the percentage of the equilibrium. So at 1.9. Okay, let's go to 1.9. So this is a place, this is a position where I get, this is a position where I get my time constant defined from myself, okay? So the tau is equal to 0.294144, okay? So if I have a tau like this, my omega 1 that I should have is equal to this expression. Okay? Yes, it will be equal to this expression. This is the omega n, and then from here, as we done previously, the omega n that has been generated randomly will be normally equal to this one if there is no mistake, so it is here. Okay? So this is what I wanted to show you. Even in this context, you have the good value, right? And then now let's go for here. If we consider that the maximum value, I'm going to zoom a bit in order to be able to consider the maximum. Okay. So we consider that we are at the maximum point here. When we are at the maximum point, the overshoot that we can compute will be the difference, the percentage of overshoot will be the difference between this point, that is, so just call it overshoot. It is equal to parenthesis 1.96378 minus 1.5, okay, divided by 1.5. The overshoot, if you multiply by 100, is around 31%. Okay, so if I check in my notes, it is an overshoot of around 31% or 30.92%. That is exactly what I have in my notes. So somebody could just proceed like this to define also the damping ratio, the corresponding damping ratio for our system. So I hope that this message is very clear for you. I hope that this message will help you go further in your projects, etc. And then again, thank you for watching. Please like, share, and then if you have any other questions, if you want us to discuss more deeply this new vision that I am introducing in control systems, you can contact me here at contact@daboacademy.com. Again, thank you. Webale, siabonga gakulu, jerejef mangilendi garambubah, and then I hope we will be able to share again another video very soon. Thank you. Enjoy your day, enjoy your time, and then see you soon.